I will be presenting on constant velocity motion. The purpose of this lab was to record the motion of an object moving at a constant speed, analyze that motion with Tracker, and then build a computational model in VPython that predicts the motion using fundamental physics principles. The key result I found is that both my observed motion using Tracker and my computational model showed that the object moving with nearly constant velocity was true. The position versus time graph for both was linear, and the velocity versus time graph was approximately flat. This agreement supports the idea that when the net force on an object is zero, the momentum principle predicts constant velocity motion. The model I used in this lab was based on the momentum principle, which is another way of stating Newton's second law. F net equals change in momentum, where momentum is defined as mass times velocity. This principle tells us that the net force acting on an object is equal to the rate at which its momentum changes. If the net force is zero, then momentum is conserved. Since mass stays constant, velocity stays constant as well. This is exactly the physical situation I'd observed in my video, and so in my computational model, I set the net force equal to zero. The VPython program then applies the momentum principle in small time steps. Each step, it calculates the new velocity and position of the object using the velocity update formula and the position update formula. Since the net force is zero, the velocity never changes, and the position increases linearly with time. This is why my plots, the position versus time graph, is a straight line, and the velocity versus time graph is flat. Seen here, these are the visual signatures of constant velocity motion. I chose this model because tracker data shows that the object's positions were equally spaced in time, meaning that the object almost had no acceleration. That justifies the assumption of zero net force in the code. So the fundamental physical principle is Newton's second law, momentum principle. And the computational model is a step-by-step numerical application of that principle under the condition of zero net force. For the experiment, I recorded the motion of a whiteboard marker moving in a straight line at a constant speed. The motion was captured on the table level view, which would be less accurate than recording the whiteboard marker travel across the table from a top view. I will discuss that in the error section. Anyways, I placed a meter stick in the frame as a calibration stick so that Tracker could convert pixels into meters. Tracker, I marked the position of the object frame by frame, giving me a table of time and position data. That data clearly showed a nearly constant spacing between points, meaning constant velocity. The computational model, I started with the provided VPython starter code. I set the initial conditions based on my tracker data. I set initial position, initial velocity, and time steps shown here. Since the object moved with no acceleration, I set the net force equal to zero in the code. The program then updates position each time step using the velocity, plots both position and velocity versus time, and then prints out the position values. Both the tracker data and the computational model show the same trend, a linear position time graph and nearly constant velocity, just as the momentum principle predicts when the net force is zero. The main difference is that the experimental data looks bumpier, while the model is perfectly smooth. This is due to small real-world forces like friction and tiny measurement errors in tracker. The model assumes an idealized system with zero net force, so it captures the essential physics, constant velocity, while smoothing out small variations present in real data. Few small sources of error. In the video analysis, tracker points were not perfectly aligned from frame, and the friction of small bumps may have slowed the object slightly. These effects cause tiny deviations in the velocity graph. Additionally, the marker's center of mass was taken at a straight angle instead of a 90-degree angle looking down at the marker. So that could have also added to the error in tracking of the marker's movement. In contrast, the computational model assumes perfectly constant velocity with no forces acting, so its line becomes perfectly straight. But overall, the agreement between the experiment and the model was strong. The what if and what does it mean questions. What if I flipped the axes? If I chose positive x pointing in the opposite direction, all the position values would be negative instead of positive, and the velocity would also have the opposite sign. But the slope of the position time graph and the shape of the velocity versus time graph would remain the same. So the physics conclusions don't change, just the sign convention. What does it mean if F net is zero? In my model, I set the net force equal to zero, but in real life, that doesn't mean that there are no forces acting. The object may have balance, pushes, and pulls, such as forward motion balanced by rolling resistance or very small drag forces. The important point is that the sum of all the forces equals zero, so that the net effect is no acceleration. In conclusion, this lab demonstrates that an object moving with a constant velocity can be accurately modeled using Newton's second law and with zero net force. Thank you for watching my presentation.